Hey everybody, welcome to lecture 6.3 on joint probability distributions. I know we're jumping around a little bit in topics towards the end of the course, but I think things are structured in the right way. We learned probability early on in the course and learned a lot about probability density functions and how to integrate them in order to compute probabilities of different continuous random variables. And we're going to do something in this chapter, in chapter 6, after we've learned double integration, how to compute volumes, and study something called the joint probability density function, or a joint probability distribution. This is going to allow us a whole new host of tools to study more complicated probability problems than we saw previously in the course. So the two goals in this video are going to be to define and learn how to integrate a joint density function to calculate a probability of multiple variables at a time. This is a multivariable calc problem. That's also a probability problem. And we'll also learn to recognize when two random variables or more than two random variables are independent from each other using our joint density functions and multivariable techniques. So this is really bringing a lot of strands in the class together. To start, let's discuss the notion of a joint density function for two or more random variables. For the most part in this video, we'll just talk about two random variables, x and y. And remember, from a long time ago, we learned that a single random variable, let's say x, represents the different numerical outcomes of performing some experiment. For example, x could represent a 0 or a 1, depending on if a coin flips heads or tails side up, and you can encode similar probabilistic scenarios using random variables like this. Those are discrete random variables, and we earlier in the course defined the difference between a discrete variable and a continuous variable, and here we'll mostly focus on continuous variables, x and y, that can take values on some interval of real numbers or potentially the entire real number line. So each of x and y have their own possible values, and we want to study the probability of certain outcomes of both of the variables simultaneously. And this is what's represented by a joint probability function. So if the space of possible outcomes for x and y together, the space of pairs of two different measurements we make, is continuous, meaning for our purposes, the entire xy plane or subsets of the xy plane, then the distribution is called the joint distribution for these two continuous random variables, x and y. And the distribution can be modeled by a function called the joint probability density function, f sub x of y, for the variables, and this is a function of two lowercase variables, x and y. Remember previously, just so we don't mix up two notation, if you cover up the y parts and just look at the x parts of this notation, f sub capital X for a random variable capital X is a function of lowercase x, and lowercase x is allowed to take on values in a certain interval of possible outcomes for capital X, and likewise here, lowercase y is representing some interval of possible values for the variable capital Y, the random variable y. So how do we define a joint probability density function? We haven't made the definition yet, but here it is. We'll call f a joint probability density function. We'll just say a joint distribution in the future if whenever we want to measure the probability that x falls in a certain range of x values and y falls in a certain range of y values, and both of these occur at once, the probability of this happening is determined by the double integral of f over those x and y bounds. So in this case, we've written it as an iterated integral, a to b, c to d, and notice that dy and dx are ordered appropriately for these integral bounds to match the probability expression, and then we integrate the joint distribution f against these bounds to determine a probability. So this is both a definition and a recipe for how to compute probabilities. F is a probability density function if it satisfies this. And if we have a probability we want to compute and we know a formula for f already that's given to us as a multivariable function, we can perform this double integral or compute this double integral to compute the probability on the left. More generally, we don't have to just compute over rectangular regions of the xy plane. And notice that fixing these constant bounds a, b, c, and d gives us a rectangle in the xy plane. We could ask for the probability that the pair of outcomes x comma y for our two variables lies in some region D in the xy plane. So this D could be the interior of a circle. This could be a triangle or the area between two curves or something more complicated that we've seen a few examples of in the last few videos. And if we ask for the probability that that pair of values lies in that region of the xy plane, then this will just be computed by the double integral over that region D of our joint function f with respect to area. And now, of course, we have to figure out how to compute this, and this is what we've been practicing so far this chapter. So a joint probability density function is our main character to study in this lecture. Let's try computing a probability using a joint density function. So here is a pair of random variables, x and y, and we're told that they have a joint density function f given by x plus y. So add the values together, and that will determine the probability. And these probabilities are only defined over the interval 0 to 1 for both x and y values. We can think of that actually as a square in the xy plane, and here I've started to draw the picture below. And the question asks us to compute the probability that the random variable x outputs a value at least twice as large as the output of capital Y. So what's the probability that x is at least twice as large as y? We can encode that algebraically as this inequality: x is greater than or equal to 2 times y. So that's just coming from the problem. And based on the previous slide, we can compute this, the space of all x that are at least as big as 2 times y is a subset D in the xy plane. And I'm just going to draw it for you in a moment below, but we know that by the definition of a joint density function, we'll be able to integrate our function x plus y over that region D. And really, I should say, I'm going to change this briefly. This should really be f of xy that we're integrating over the region. And in certain places, it will be 0 if we're outside of this square that we've drawn. So let's draw the region D, which is x is greater than or equal to 2y. Well, if x were equal to 2y, that'd be the same as y equals 1/2 x. That's a line through the origin of slope 1/2. And I'm going to draw here. And this is y equals 1/2 x, or x equals 2y if you like. We're trying to study for which x values the xy pairs, the x coordinate is greater than or equal to 2y. And you can test on both sides of the line and figure out that it's this side of the line. But notice that the only place where the probability density function is non-zero is inside of the square with vertices 1, 0, 0, 1, and 1, 1. That's our domain of that's the domain of the function where the x and y values don't give 0 necessarily. So inside of this small triangle, the area between the bottom of the square and the top of the line that we drew, this will be where we need to compute our probability. Again, we're not capturing anything on this side of the line because that's not the probability we're looking for. And anything outside of this box down here has 0 probability according to the probability density function. So now we're down to the following double integral problem. We've reduced things to an irregular region, or a region that's not a rectangle, and we want to compute this. We want to compute this volume of this function to compute a probability. So how do we do that? We need to parameterize this region, and I see I've already written it in 2 ways: as x as a function of y if we need, or y as a function of x if we want. And if you decide between doing dx or dy first, you'll notice that if we integrate with respect to y first, we already have a top and a bottom function. So I'm actually going to write the inside integral first, and then we'll figure out the bounds for x on the outside. They're pretty easy though, so I probably don't even need that much room. The inner bounds, which will be y bounds, are x is ranging from 0, that's the x-axis, up to this line, which is 1/2 x. The function we're integrating again is x plus y, our probability density function, and we'll integrate with respect to y on the inside. Then we'll do x on the outside, and notice that x just ranges from 0 to 1. That one was pretty easy to figure out. I encourage you to pause the video right now and try to work this out by hand to practice the material from the previous section, calculating double integrals over irregular regions. And notice that we have a function in one of the bounds of the inner integral, and that's okay, we can handle this. So once you've worked this out on your own, I'm going to start working it out for you now, and you can check your answer against this. So pause now if you don't want to see the answer yet. To perform the inner integral, let's keep the dx stuff on the outside the same. We're going to integrate x plus y with respect to y. which means we'll pick up a y in the first constant term, and then 1/2 y squared by the power rule. And we're integrating from 0 to 1/2 x, so that's what we'll plug in the next step. I think I left enough room. Let's still integrate from 0 to 1 on the outside, but first of all, let's figure out what happens on the inside. When we plug in y equals 1/2 x, I'm going to get a 1/2 x squared in the first term. Let's see, 1/2 squared gives me 1/4, so that constant will be a 1/8 in total, and then an x squared will happen. We can actually simplify this a little bit. I'll take another line to do it. And by the way, notice that plugging in y equals 0 just gives me 0. I skipped saying that out loud, but I don't need to plug that in to write anything down. Let's simplify things a little bit. I have 1/2 x squared and another 1/8 x squared, so that's 5/8 times x squared. This is definitely an integral that you can compute, and I will tell you the answer. I'm using a little bit of my experience computing integrals like this to give you a quick answer, but the probability will be 5/24. And just for a numerical answer as a decimal, it's about, let's round it off to 20.8% probability. Good. So that's our first computation of a joint density function in order to compute the probability that a certain outcome occurs between the two random variables. So given two independent random variables, it's important that these started with completely independent probabilities. We can actually measure the dependence on these variables by calculating some probability in the xy plane using our joint density function that we're provided with. All right, let's get back to it. So here's a quick warning. If you were to just compute the area of that small triangle that I shaded in green during the previous problem, you would see that it has an area that's 1/4, well, that's 1/4 units, which is 1/4 the total area of the square of side lengths 1 and 1. However, we didn't just get 1/4 of the total probability. And this is because different points inside of that square where our function has non-zero value, our density function had non-zero values, have different likelihoods or different probabilities of occurring. And that's because the probability density function was x plus y, not just a constant uniform random variable over that square. So just computing areas is not good enough. We really do want to compute double integrals of density functions in order to tell us about probabilities. So because 5/4 is a little less than 6/4, which would be, 5/24 is a little less than 6/24, which would be 1/4 of the total area, we see that in that bottom right corner inside of the triangle we shaded, the possibility of x being greater than or equal to 2y and landing in that triangle is actually slightly lower than just a uniform random variable would predict. And this is based on, again, the probability density function with x plus y instead of a uniform variable, but I just want you to not confuse the notion of area in the xy plane versus the notion of the integral of a density function. Here's an exercise. I'm not going to work any of this out with you, but we can certainly do this in class together or for exam review if people have questions. And in this problem, we're given another joint density function, this time describing different arrival times for two friends, Dharmak and Jalad. So if these two friends, or I guess, okay, maybe they're not friends, they're just strangers, but let's pretend they're friends for this slide. If these two friends travel to the island of Tanagra together and arrive sometime between noon and 4 p.m., we can measure and assume they arrive at some random time or some probabilistically determined time between noon and 4 p.m. for each of them. Then we can let their arrival times be represented by continuous random variables x and y that range over the values 0 to 4. If we call noon 0 o'clock, or just time 0, and 4 hours later, and likewise for Jalad 0 to 4, then we can ask for what probability are these two arrival times related? What are the probabilities describing different regions of that square with side lengths 4 and 4? And we're given this density function. So first of all, the problem asks you to compute the value of this double integral. And actually, I want you, when you're doing part one, to interpret what this double integral tells you in terms of the given probability problem. The next two parts ask you to calculate the probability, two different probabilities inside of this square by using double integrals. First, the probability that Dharmic, the x variable person, arrives before a certain time. And next, a little more complicated, the probability that Dharmic arrives before Jalab, and that's going to be described by a non-rectangular region inside of the square that we're given in the probability problem. And parts 4 and 5 ask you to interpret a little bit more what the distribution says about which person is more likely to arrive before the other one, and then to set up an integral that describes their arrival times in relation to each other. So this is an exercise. It's worth working through on your own. I'm going to move past it for now. The next thing I want to talk about is the notion of a marginal density function. And just in words before we get into the mathematics, when we have two random variables, x and y, such as in the previous problem with two arrival times, or two just different scenarios that we want to measure their joint probability together using this function, we can ask about each individual variable separately from the other one. And if we just want to extract information about a single random variable and let the other variable take on any possible value, this is the notion of a marginal probability, or what we'll use to measure this, a marginal density function, a marginal distribution. Notice if we have a single random variable x, and we maybe have another random variable y floating around, but we just focus on that random variable x, that we know how to integrate in order to compute probabilities. If we're given a density function f sub x just for that single variable, capital X, then to compute the probability that x lands in a certain interval of x values for the variable, we just have to integrate from a to b this density function. And the question is, if we have a joint density function for x and y together, how can we extract that single variable density function to compute probabilities just for x alone? Well, if you think about this geometrically, the probability that just the x variable lands in a certain interval of x values is geometrically equivalent to the region between the vertical x lines, x equals a and x equals b, which is an infinite strip in the xy plane. So this is asking for any possible y values. Let's add up the probabilities where x lies in this region. This is an infinite rectangle. We can actually compute this probability using an improper integral on the dy part of the integral. So here's the notation. I want to dig into this notation a little bit more. If we have a joint density function or joint distribution set up that we can compute using double integrals, and we want to just extract those density functions fx or fy, this will actually be the inside integral in our double integral. And notice that the thing I've shaded in this blue box is exactly the same as the thing that should go inside of our single variable density function just for the variable x. So why did that skip around? Here we go. So we'll call these marginal density functions the individual fx or fy for one variable at a time. And the way that we compute them, and really the way that they should be defined in multivariable calculus, is as an improper single integral of the joint density function f with respect to just the other variable y over the entire y-axis. So that'll give us our x variable. And imagine this as being this rectangle that we're integrating over. And likewise for y, if we took a horizontal infinite rectangle where x is allowed to range over any values, and we just want to pick up the y variable's density function, this will be the marginal density function with respect to y. So the notation is exactly the same as we used in our earlier studies of single variable density functions. And that's because this is truly a density function for fx. It's just written as an improper integral over the entire range of y values. Notice that there's still an x variable, and as the inside of a potential double integral, it'll still be a function of just x. Likewise for the y expression. So how can we possibly interpret this in a more geometric way other than just integrating over those rectangles? You should think of this as choosing an x variable or an x value x naught and looking at just the inside of the double integral expression at that particular x naught value. So what this looks like is if we look at this improper integral where we've plugged in a particular x value, then this double integral, or sorry, this single improper integral with respect to y is picking up the area of the cross section of the joint probability function at that fixed x value. So if I fix an x value here, we look at a cross section, maybe this gold plane of the joint density function z equals f sub xy, then the area of this gold shaded figure will actually give us the value of the marginal density function at x naught. And if we slide x around to get different values, that'll tell us the possible outputs of the marginal density function for x. So this is just a quick geometric interpretation using cross sections, but in practice and in this next problem that we'll do together, we'll just do this algebraically and using calculus by setting up an improper single variable integral. So here's another problem we're going to do together. Let me switch over to start setting things up for you. And I'll break it into a few parts. You can rewind the video a bit to see all 4 parts together if you like. So to compute marginal density functions, let's consider the following setup. Students at schools around the world, especially in like a physics class in middle or high school, often will construct rockets to learn about physics and velocity and acceleration and trajectories and things like this. So let's say some students around the world all come together and compete in a rocket contest. And rockets are scored in this contest based on just the pure altitude off the ground that they reach, let's say in meters to give it some units. And let's suppose that the first and second place altitudes for rockets among all of these schools can be modeled by continuous random variables x and y. So if we choose a random school and pick out the first and second place rocket altitudes just in that school, then these rockets x and y have altitudes given by the variables x and y, but the joint density function tells us among all of the possible schools how likely it is to choose first and second place rockets with these given altitudes. So again, this is a probability density function shown here. Notice I want to point out the x and y range is something we'll draw in a moment, but it's a closed and bounded subset of the xy plane. And then the density function says 0 outside of that region. So there's no probability of selecting first and second place value altitude values that aren't described by these possible values. And I want to just start stepping through this problem and interpreting a few things. So first of all, given the presented information, what can we infer about the possible altitudes of student rockets just by looking at this density function? And let's state it in terms of what's the maximum possible altitude of any of these rockets among all of the different schools. Well, if we let the first and second place be modeled by the variables x and y in that order, then we see that x is constrained just by the numbers 0 and 1,000, which says that, well, the minimum altitude is 0, but I'm sure that has low likelihood since some of the rockets will get off the ground. But the maximum altitude for x is 1,000 meters. So among all of the possible schools, that's the highest x value, the highest first place score that has any non-zero probability of occurring. So the highest maximum altitude of any of the schools is 1,000 meters. And on the other hand, given that first place score, we know the second place score can't have beaten it. So the y second place variable is no greater than x. And again, it can't be lower than 0. It didn't shoot into the ground. So the second place maximum altitude is less than or equal to the first place. And also, theoretically, could also be 1,000 if we take the first and second place to be in a two-way tie. And that's just the way that the region is set up to be closed and bounded. But theoretically, we would have some tiebreaker, or we'd have precise measurements to distinguish first and second place. So the second place maximum altitude, depending on the first place altitude, can range from 0 up to that first place number, and the first place altitude can range from 0 all the way up to 1,000 meters. Next, let's compute the marginal density function just for the x variable. Let's say we're only interested in first place top altitude scores from each of the schools, and then maybe we want to collect all of those and compete just with the first place scores. So let's find the marginal density function for the altitude of the first place rocket. And in words, this is a density function that measures the probability that if we choose a random school, its first place score will be this given altitude that we plug into the function. So x is an altitude, and it's the output of the random variable, just the first place score, and then integrating this function will tell you probabilities. So to compute a marginal density function, from the previous slide, we learned it was the improper integral from negative infinity to infinity with respect to dy of this function. Now this is a function of x and y, but when we integrate out the y part, we'll just be left with a function of x as we expect. So I've put our density function from the problem into our improper integral. And notice that it actually doesn't become an improper integral since the f of xy values in the function description are only non-zero between for x values ranging from 0 to 1,000. We are not integrating anything else for dy. So, we are integrating all y values. So the only place where, once we've chosen our x value, the y output, or the y variable gives you a non-zero probability, is when we have the second place score ranging from 0 up to the first place score. If we integrated past 0 to the left, if we went down to negative infinity, we would just pick up a bunch of 0 probabilities. And likewise, if we let y, the second place score, range above the first place score, there would be 0 probability of that occurring. So we can restrict our integral just to this single variable, now proper integral. We have a variable in the exponent, but that's okay. Let's do our ordinary process of integration. So this looks complicated, but notice we're integrating with respect to y, since there's a dy. And the only place that y shows up is here and here. Every other expression is a constant. So in fact, I'm going to copy this leading coefficient into the answer. This is a constant with respect to y. And we don't have to do any quotient rules because the denominators of these two fractions in parentheses are just x terms. So those are constants. And we just have to carefully integrate with respect to y in each term. Y turns into 1/2 y squared. So I'm going to write y squared over 2x squared. And y squared becomes 1/3 y cubed. So I'll write it y cubed over 3x cubed. And finally, we're going to evaluate this from 0 up to x. This is going to dramatically simplify the expression. Let's take another step or two to do it. So we'll have our leading fraction, which is still a function of x. And in parentheses, if we plug in x, well, plugging in x for y is going to cancel some x powers out. We'll have x squared over x squared gets canceled. We're just left with 1/2. And y cubed over, or x cubed then over x cubed cancels. We'll be left with 1/3. And I'm going to simplify this with one more step. 1/2 minus 1/3 is 1/6. And if I see a 12 in both expressions in the top, so I'm just going to divide those by 6, and I'll be left with 2 minus 0.002x all over 1,000. There are different ways to simplify this, but I like this one the best because I can cancel some 12s and 6s out. And this is, again, the marginal density function for x, the first place random variable. Another way to interpret this is if we randomly select a school and we plug the altitude of its first place score, if we randomly select a school and we have a particular altitude in mind, the probability that that altitude is achieved is obtained by integrating this function over the possible altitude range that you want. So if you make that range of values really small and just a little bit to the left and to the right of a particular altitude, that's basically capturing the probability of that altitude occurring. Okay, let's keep interpreting things a little bit. So we just determined the marginal density function for capital X. What can we conclude about the values of X where they're more or less likely on the range of possible first place values? We know that the total range from 0 is from 0 to 1,000. So as we increase the possible altitude output from the experiment or from the contest, for the first place, the probability of a first place score at a random school getting a higher altitude actually decreases as we increase the altitude. You can see this from the function, or you can even take a derivative with respect to x and so you get a constant negative number, negative 0.002 over 1,000. That's going to be some small negative number, but the probability marginally decreases just with respect to x. as we increase the x altitude. That's actually, let's see, that's all we're going to do for this problem. Let me make sure I didn't skip part D. I thought there was a part D. No, actually, this was it. Other things you could ask in this situation are, what about the marginal density function for y? Namely, if we just focus on possible second place altitudes, can you write down a single probability density function that measures those? And it's going to be a little more complicated, basically because we'd have to draw this region. This is a triangular region in the xy plane, and compute an improper integral for the x values over this region. And sorry, I didn't mean to skip back. Things are really skipping today. I apologize. We'd have to reparameterize the region to be able to write down a single variable improper integral with respect to dx, and then compute that in order to generate a marginal function for y. That's a little more complicated of a probability expression because it's telling you among all possible second places what their likelihoods are. But of course, those are really predicated on the fact that they have to be no larger than the first place score. So it's a little easier to interpret the first place marginal density function that we determined. Let's talk about expected, sorry, first, one more comment, by the way. Marginal density functions are areas, not volumes. And a couple slides ago, I had that cross-section interpretation of marginal densities. You should again think of taking a cross-section at a particular x value, and then the the possible y values are then just constrained by the area under the graph, or the area of the base region where our density function has non-zero values. And given those possible y values, we have a range of possible outcomes, but the total area of that cross section over those y ranges, shown here as this little gold sliver at this fixed x value, that total area is the output of the marginal density function just for x. So even though the range of possible outcomes for in the previous problem was larger for x, the probability of actually achieving that x is smaller. And we saw that in part C, we interpreted that the probabilities decrease as x goes up. And this is, if we graph the function in the previous problem, this complicated looking expression for x and y, as a two variable function, there's going to be an issue at the origin. There's really an asymptote. But the probabilities really flatten out as x increases. And you can see that with lower height on the density function, these data points out here, these possible first and second place scores, have much lower probabilities than the lower altitude scores. So there are a bunch of dud schools with a bunch of dud rockets, and I guess those students didn't do very well. Things are more likely to happen down here at the lower end. But these really stellar rockets that are achieving 1,000 meters of altitude are much less likely, and they occur here on the tail of the distribution. And this is just a recap of the main ideas from marginal density functions. In order to extract information about a single variable, we can still use a joint density function and perform an integral with respect to one variable at a time, rather than computing the entire double integral. I want to talk a little bit about dependence versus independence. And I'm sorry, we're going to talk about expected value, but that's later in the video. I was just jumping ahead in my notes. Sorry. Is this? Oh, good. Okay. Sorry, my computer is pretty old on this end, so you've seen me click around a little bit today, and I'm going to blame it on the computer. So you might have this question of, why do we need joint density functions? Why can't we just integrate one of the variables against its possible x range, and then the other variable against its possible y range, and then do something with those values? Well, we've already seen that even in the previous problem, when the second place score is really constrained by what the first place score is, that the probabilities are also constrained or depend on what the possible variable outcomes can be. However, if x and y are independent, meaning the probability of x achieving a certain value is independent of anything happening on the y side and vice versa, then we actually don't need a full joint distribution to compute things. And the way to say this using some familiar double integral terminology and symbols that we've seen is that the variables and their density function can be multiplied. So we will call two variables x and y independent if their outcomes don't depend on the outcomes of the other variable. So this is just a general terminology. You can think of this as like the English definition of independent. What does this mean mathematically? If the outcomes don't depend on the other variable, then the probability that x takes on a certain value in the range a to b and y takes on a certain value in the range c to d can actually be computed as just the products of their two independent probabilities. The density function for x, really the marginal density function, will just have its own single variable integral, and same for y. And if you remember from our study of double integrals, this is one of the possible ways of computing a double integral when the joint distribution function, in this case, the double integrand is the joint function, can be factored as a product of two functions, one just a function of x and the other just a function of y. So another way to say that x and y are independent variables is to say that their joint probability function is a product of two functions, the joint function for x and the joint function for y. And if you want to compute those joint functions for x and y, those marginal functions for x and y, whose product is the joint function, you can do so using the marginal distribution formula a couple slides ago, where you take an improper integral with respect to the other variable. So independent variables, we usually say in probability theory, with independent variables, their probabilities are multiplied. And this is an integral expression for that fact. So let's look at our arrival time problem again. This was the exercise that I hope you had a chance to work out before. You can work out the mathematics for that later, but just remember that we had two friends, Dharmik and Jalad, traveling to the same island, I forget the name, and we want to measure the probabilities of their different arrival times. Let's suppose that their arrival times are independent of each other. And in fact, we can see that they're independent because this function, the joint probability function, factors as a product of two separate single variable functions. The x function is x over 32, and the y function, you don't see any y's here. That means we can take y to be the constant function 1. What does this say in words? Well, Jalad, whose arrival time is represented by the y variable, has a solo or marginal density function for his arrival time given by the constant function 1. This actually means that as a single random variable, Jalad's arrival time is uniformly distributed. A constant density function corresponds to a uniform random variable. On the other hand, Dharmuk's arrival time is triangular, which you can, if you draw this region and draw this density function as the height over that region, you'll see that there's sort of a triangular looking shape, and more specifically, the cross sections of these shapes to compute the marginal density function for x for Dharmuk's arrival times are triangular cross sections. In the y direction, the cross sections are rectangles, which are uniform distributions. That's a characteristic sign of a uniform random variable. But in either case, we can separate these joint distributions into two functions. Neither distribution will depend on the arrival time of the other. And that means that their arrival times are independent as random variables. So we can compute any possible probability of these two arrival times in relation to each other just by multiplying their probabilities independently. Here's a quick theorem about, this is just really a theorem that's expressing what I said 2 slides ago about the joint density function for two independent variables. And the theorem says that if x and y are independent random variables, rather they are independent if and only if their joint density function can be written as a product of two single variable functions, g of x and h of y. And more specifically, g of x and h of y can be chosen to be the marginal density functions of x and y. Notice that they don't actually need to be exactly those marginal density functions, because if we had g of x, and I'm going to go back to the previous slide to show you this, if g of x were x over 32 and h of y were just 1, we could come up with a different pair of functions, single variable functions, by moving that 32 over as a constant into the h of y expression. So we could have g of x is x and h of y is 1 over 32, and that would still give us a factorization into a product of two single variable functions that we're asking for in the theorem. So these are not unique, and they don't just have to be the marginal functions, but it's actually useful to think of the two individual functions as marginal density functions for the two variables. Okay, here's another example using marginal density functions and using independent variables. If you're given a joint density function for two random variables and you're asked to find out if this is a pair of independent variables or not, all you have to look at is, at least in this case, where the functions are non-zero. Over this range of x and y values, we can separate the function into two individual pieces, and you'll see that these are actually the marginal density functions if you were to integrate the relevant improper integrals to compute marginal functions. The fx marginal function is this pi coefficient times cosine of pi over 2 times x. That's just the x portion of the joint function. And it's just that for the range of x values given, it's 0 otherwise. Likewise, if we factor out a 3/4 from this expression and pair that with the y expression, 2y minus y squared, this will actually give us the marginal function for y. Notice that just taking from left to right all of the stuff with constants and x's, and then stopping and throwing the rest of the y expression into the y marginal function won't actually exactly reproduce the marginal functions, but it still shows that this joint function is factorizable as two single variable functions, and therefore the two variables x and y are independent. It's a little stronger to actually compute the marginal density functions using improper integrals, and this isn't so bad of a computation if you want to work through that on your own, or we can do this in class or during exam review. Here's another visualization of the previous problem. If you were to graph this joint density function with the cosine and the nasty coefficient, you get some wave-like looking surface like this. And independence of these variables tells us that at any given fixed y value, the probabilities in the x direction are independent of which y value that we chose. So if we want to compute any integration just of the marginal density function for x, which is just happening in the x direction, it will be the same no matter where we stuck our y value and slid it around. So this is an example of an independent joint density function. And again, you'll see that the cross-sectional areas are the same over certain ranges as we shift left and right. It appears that the cross-sections change in shape as you move left and right, and that is true, and that's because this function is not constant in the y direction. Change in the y value gives you a different height. However, what's important and what's really mysterious just from this graph, but totally transparent when we factor these two functions and sort out their independent probabilities, is that the areas over any x region of any of these cross sections as we slide the cross section in the y direction will be the same. And that's sort of a miracle. You can think of this as a family of cross sections whose single variable integrals in the x direction are all the same no matter where you take your interval of x values. All right, let's now talk about expected value. So expected value for a single variable function, a single continuous random variable x, was computed by integrating the variable x times the density function. And we can do something more complicated with multivariable functions, which is really the notion of if we combine the outputs of the two random variables x and y, we can ask for the probability of that output variable landing between two different variables, landing in a certain range of possible joint outcomes. This is a hard problem in general. And for example, if we look at the single variable, or if we look at the two variable function g of xy that spits out a single real number as an output, let's say y squared over x, we can ask for the expected value of this function, which is really a function of two random variables. And you'll have to look back at our section on functions of single random variables to recall why this was important. But we'll have real world problems that actually pertain to this technique. So if we wanted the expected value of this function of random variables, this is a hard thing to work out in general. And what we'd have to do is work out some density function h, whose integral describes the probability of this function of y and x landing in some range a to b. So we can do a little bit of math, and I'm going to skip over this part. You can read a little more in the book to determine the following. And here's, by the way, here's a graphical representation of that expected value problem for the arrival time of the two friends traveling to the island. We have to work out some function h, whose integrals actually express the areas in this blue region. And this is a difficult problem in general. However, we have the following theorem that allows us to compute expected values of functions of two random variables, x and y. And we can dodge the issue of producing that new density function h by using the expected value theorem, which expresses things as an integral of the product of two functions, just like we did in the single variable density function study. So here's what the theorem says. If we have two continuous random variables, x and y, and we look at a function g of x and y, such as y squared over x on the previous slide, if x and y have a joint density function f, then the expected value of this function of random variables, g of x, y, can be computed as the improper integral over all possible x and y values, or the double integral over the entire xy plane of g of xy times f of xy with respect to dx and dy. And we can, again, by Fubini's theorem, as long as these improper integrals converge, we can reverse the order. Here's an example. Let's go back to the, let's see, I already forget what scenario this was. Let me remind myself. This was not the rockets. Oh, this was the rocket problem. Yeah, I'm sorry. So let's go back to our rockets and ask for the expected value of just the first place altitude random variable. So given this probability density function for first and second places, and given that we just are interested in the first place scores in the contest, what's the expected value? What's the overall average first place score among all of the different schools competing? And the theorem in this case simplifies dramatically. Our function here, if we want just the expected value of a single variable x, we're really looking at the function g equals just x by itself. That's a much simpler function than could happen with different problems. So we're asking for the expected value of the expression capital X, which is secretly a multivariable expression, but it only depends on one of the variables. And the theorem for expected values tells us to integrate over the entire xy plane of that function x times the joint distribution for these two random variables. That's our f expression. And let's try to compute this by hand. So I've copied the joint density function in here. We're just going to multiply that through by x, but I want you to notice something. If we integrate with respect to y first, which we'll need to do since we're going to plug in our actual ranges for non-zero probabilities. Again, x is ranging from 0 to 1,000. Let's leave that as constants on the outside. And y is ranging just from 0 up to x. This is now no longer an improper integral. On the inside, we want to integrate with respect to y first. And notice that x is a constant with respect to y. So I can move that all the way outside of the dy integral. And what I'm left with is actually an integral from 0 to x of this function that we've seen before. This is exactly the joint distribution function. And that's actually what we used in the previous problem to compute the marginal density function f sub x just for the variable x. So I'm going to write this another way. All of the things that I'm about to circle in blue, this piece, and just this piece, including dy alone, give us this marginal density function f sub x, which we already did the work to compute in the previous problem. So we'll still need to multiply by x. Remember, I moved that out as a constant with respect to y, but the marginal density function that we got is this expression. You can go back and check your notes if you don't trust me, but we just need to multiply this expression through by x and integrate that resulting expression from 0 to 1,000. Notice that this whole integral here really is just the expected value of the x variable by itself. And we'll have this as a takeaway on another slide in a moment, that if we want to compute the expected value of a single variable at a time, we just have to determine the marginal density function, fx or fy, multiply by x or y, the variable we're interested in, and then integrate that over the possible ranges for that variable. That's going to give us the expected value of that variable. However, we'll see in another problem shortly that we can look at expressions like the expected value of y squared over x, like we saw on the previous slide, and that will be more complicated and won't necessarily just be determined by a single marginal density function. So I'm going to leave it as an exercise for you to compute the value of this integral, to compute the expected value and really the average rocket altitude in that problem. And let's move on and wrap up a couple more things. So here are some main takeaways from this discussion of expected values. What we learned in the previous problem, and really if you look closely at the theorem, this is directly from the expected value theorem, is that the expected value of a single variable at a time, either ex or ey, is given by the double integral, by definition, the double integral of x times the joint function with respect to dy and dx, and for y it'll be y times the joint function. However, the inside integrals in both cases, we can factor out the other variable x, and in this case we can factor out the y, switch the order, so dx is being integrated first and factor out the y, and then use the inner integral, which is really the marginal density function for one of the two variables by definition, and condense this formula down to the single variable expected value formula. Now, secretly, this fx single variable marginal density function is itself computed as an integral with respect to y, and likewise for e bracket y, the expected value of y, but we can use this as a faster method for computing expected values if it's only for a variable x or y, one variable at a time. And the work required in these problems is basically the same as if you start from here and do a little bit of factorization and integrate versus already having that marginal function. But there are some corners you can cut once you have the marginal function if you want to just go straight to this formula. Let's go back and talk about the arrival time joint density function for Darmok and Jalad arriving on the island, and compute the expected value of this variable y squared over x. Given this same density function over the rectangle 0, 4, 0, 4, we want to figure out what the expected value is of the ratio of Darmok's arrival time squared divided by Jalad's arrival time. Whatever that means in plain language, that's the variable that we want to compute an expected value for. And we're just going to practice with this once setting up the theorem. Okay, so by the theorem for expected values, and in this case, this expression is our g of x comma y, we stick a g in front of the joint density function and take a double integral over the xy plane. So the only place where x and y both give us non-zero probabilities is if they're both between 0 and 4. So luckily this is a rectangular double integral problem, and it's not one where we have to have variables in the bounds for the integral. And let's just plug in our whole expression. The joint function here is x over 32. And I'll leave it as dA for a moment. Notice that this integrand simplifies quite a bit in complexity because the x's cancel out and we just have 1/32 y. I'll leave it up to you to integrate this with respect to x or y first. This is at this point a pretty easy double integral problem to solve. It's a rectangle, there's only one variable involved, and it's a power rule problem for the integral with respect to y. By Fubini's theorem, you will get the same answer if you start integrating with respect to x or y. So it's up to you to choose which one to do. And I'll leave it as an exercise for you to compute that. That'll be the last thing that we work through together in this video. So let's just have a couple recap notions here. We can relate all of our discussion of multivariable joint distribution functions to some familiar terminology from the single variable distribution function section that we did. And one of these concepts that carries over is the notion of a uniform distribution. A uniform distribution over a region D in the xy plane is a probability distribution for two variables whose joint density function is a constant over that region D and is 0 outside of the region D. If you work out what the probability, the definition of a probability density function says about the value of this constant, you'll see that the value of f of xy, which is supposed to be constant, has to be 1 over the area of D if we're inside the region D. The reason this is true is exactly the same reason that a uniform distribution in a single variable interval from A to B has to be 1 over the length of the interval, or 1 over B minus A. The reason is that when we integrate this function, we want to integrate over the entire xy plane and get a probability of 1 or 100% probability that something happens for these two variables. If you work out the area formula using the double integral expression for a joint density function, you'll see that you need to divide by the area of D inside of the region and then set the probability to 0 outside of the region. So this is a uniform distribution for two variables. Just like we can compute with single variable functions using integrals to find average values of functions, the average value or the expected value of a given function over a region D is the expected value of the random variable f given by the function of two uniformly distributed random variables x and y. And if we want to compute the average value of a function using calculus, this will be 1 over the area of D divided by the double integral of that density function with respect to area. And another way to compute the area of D, as we saw in the previous lecture, to compute an area is really to compute the volume of a constant 1 unit of height region in the XYZ space. And if we use that double integral expression for the area of D, we'll see that the average value of a multivariable function is always computed as the double integral of that function over the region D divided by the area of the region D, which can also be computed as a double integral of the function 1 over that region. So this is a fancy way of writing the average value of a function, but in practice, this might be the only way that you have at your disposal to compute the average value of a multivariable function. I'm also going to mention something called covariance and correlation, which show up in higher dimensional statistics and probability that we don't really see in single variable statistics and probability. Let's suppose we have two independent random variables, x and y. If they're independent, the outcomes of x don't depend on the outcomes of y, and we can write the joint density function, again, as a product of g of x and h of y, two single variable functions. The notion of covariance is actually defined as follows. The variance or the variance of a single variable is, again, the square of the standard deviation, and this is computed as an integral of just x minus the mean or x minus the average value squared times the density function in a single variable case. To compute a covariance of two variables, instead what we do is we multiply the differences x minus its expected value and y minus its expected value times the joint density function, and then compute the double integral of that expression over the entire xy plane. So this is a definition of covariance that I haven't given you before. We're not going to delve too deeply into this concept, but if we have two independent random variables, then we'll see that their covariance is actually 0. So covariance will then be a measurement of how dependent two variables are. And here's a quick calculation using the notion of independent variables where we can split our density function into two individual density functions. And you'll see that the two factors you get in the two separate integrals, once you take the product of these x and y expressions separately, actually gives you 0 because this is the definition of the expected value of x. And likewise, this is a definition of the expected value of y. The key here is we can actually choose g and h to be the marginal density functions for x and y. So we'll get 0 in these expressions. So the covariance of two independent variables is 0. A joint distribution could have large covariance if the variables are dependent, or in other words, correlated. But they could also have a high covariance if the variables are dependent and there's a high variance in either of the variables individually. So there's a way of controlling for this. And again, I just want to throw these concepts out there so that you've seen them at least once. But we won't go too deep into any of these. The notion of Pearson's correlation coefficient is a way of measuring the covariance of two variables that is only dependent on each other and is not sensitive to the independent, each of their individual standard deviations or variances. So computing a standard deviation is a matter of coming up with the marginal density function, taking the variance formula, which is an improper integral, as we saw in a long ago lecture, and then taking the square root of that value. If you multiply their two standard deviations for x and y, and put that in the denominator under the covariance of those two variables, you'll get something called Pearson's correlation. And it's going to tell you a value between -1 and 1, which measures how well correlated two random variables are to each other. So covariance describes the overall spread of the data as a multivariable distribution, as a joint distribution. And Pearson's correlation tells you out of all of that spread, this is why the values are correlated with each other, not just spread out with high variance as independent variables. So that's a lot of information, and this was one of our longer videos, but here's a quick set of summary questions to get you thinking about these before we do some more work in class. First, how do we use a joint density function to compute probabilities of a certain set of outcomes? What is a marginal density function, and how do we compute it for each of our for each of our random variables? Next, what does it mean for two variables to be independent? And what does it mean for two variables to be dependent? And how do we tell when this is the case? Finally, how can we tell from the graph of a joint density function that two random variables are independent if we don't necessarily have a formula for their joint density function? I'll leave you with a practice problem. So pause the video now if you want to work out this practice problem. We've seen this picture and we've seen this density function before. This is just asking another question about it. And that's all for today. Thanks for tuning in for this long video on joint probability density functions. This gives us a lot of techniques to work with as we go forward and finish this course studying some more probability theory. So thanks for tuning in, and I'll see you next time.